Last period we have studied introduction to spectroscopy, nature of electromagnetic radiation, what is the spectroscopy, and today we will see here the some points, that is the characteristics of the electromagnetic radiations, amplitude, wave number, energy and their relationship. The next point that we will see here, the different units of measurement of wavelength and frequency, and the next one, different regions of the electromagnetic radiations. Now first of all we have to see here the characteristics of the electromagnetic radiations. The last period that we have already studied the one of the parameters, that is the frequency and the wavelength. Now we will see the amplitude, wave number and energy and their relationship. Now the next one, see here the wave number. Now what is the wave number? Already we know that we have already studied in the 12th standard the wave number. Wave number, it is denoted by the letter the nu bar. It is nothing but it is the reciprocal of wavelength. Last period that we have studied what is the wavelength. The reciprocal of the wavelength is noted by the letter lambda, and therefore the nu bar is equal to 1 upon lambda. It is also called as it is the number of the cycle or the wavelength per centimeter distance, and it is called as the wave number. Now the next wave parameter that we have to see here, the amplitude, the maximum displacement of the wave from the x-axis. Now see, this is the x-axis, see here this is the x-axis, and the displacement of this x-axis from this of the wave from the x-axis, and that is called as the amplitude, that is called as the amplitude. Now we will see the next one is the velocity. Velocity is nothing but it is of the velocity of light. Already it is the constant and it is equal to 3 into 10 raised to 10 centimeter per second or 3 into 10 raised to 8 meter per second. It is very useful to calculate the frequency as well as the wavelength. Now what is the velocity? The distance travelled by the wave in unit time, that is called as the velocity. Now see, the next one is the energy. The energy is nothing but the emission or the absorption of the electromagnetic radiations is quantized, and each quantum of the radiation is called as photon or the quantum. The electromagnetic radiation is made up of the distinct particles and it is called as the photons. Now energy is given by the equation E is equal to h nu. Nu is frequency, h is the Planck's constant, and the Planck constant is the constant and it has been given by 6.62 into 10 raised to minus 34 joule per second, or 6.62 into 10 raised to minus 27 ergs per centimeter. But we know that the nu is equal to C upon lambda. Therefore, we can write here the E is equal to hc upon lambda, because we know that the nu is equal to C upon lambda. Put this value, then we will get here the E is equal to hc upon lambda. C is the velocity of the light and h is the Planck's constant, and both are the constant. Therefore, E is equal to constant upon lambda. That is, E is inversely proportional to the wavelength. Now what it indicates? It indicates that as the energy increases, the wavelength decreases, or wavelength decreases, then energies increase, or vice versa. That is, the energy of the photon varies directly with the frequency and inversely proportional to with the wavelength. the unit of this energy, that already we know that it is measured in ergs, joules, and 1 joule is equal to 10 raised to 7 erg. Now next we will see here the different units of measurement of wavelength and frequency. See here that we have already studied the wave parameters, and we have to study here the different units of the wavelength and the frequency. The wavelength is measured in the micron, that is mu, then nanometer, nm, millimicron, mu, angstrom, that is a micron, nanometer, millimicron and angstrom. Now we have to see here the conversion, how to convert 1 micron into the centimeter. Now see here 1 micron is equal to 10 raised to minus 4 centimeter. How will convert 1 nanometer into centimeter? The 1 nanometer is equal to 10 raised to minus 7 centimeter. Then 1 millimicron is equal to the 10 raised to minus 7 centimeter, and 1 angstrom is equal to 10 raised to minus 8 centimeter. And 1 angstrom, that is nothing but 1 angstrom is equal to 0.1 nanometer. Now this is the conversion. We can use out of this one of the unit for the wavelength. Now see the frequency. Frequency is noted by the nu, and it is unit is the cycles per second, that is the CPS. It can be measured in hertz, megahertz, that is the FHZ or Fresnel. 1 hertz is equal to 1 CPS, and 1 megahertz is equal to 10 raised to 6 CPS is equal to 10 raised to 6 hertz, and 1 Fresnel is equal to 10 raised to 12 hertz. Now see the wave number, that is noted by the letter nu bar. It is a reciprocal of the wavelength, and wavelength is measured in centimeter. Then you can write here the unit of the wave number is per centimeter, or the Kessar, that is the per centimeter, and 1 Kessar is equal to 1 per centimeter. Now these are the units measurement for the wave parameter. Now we will see the next point is that different regions of the electromagnetic radiations. Now here see this, the electromagnetic spectrum, what it indicates, that it shows that the cosmic rays have the shortest wavelength and highest energy. See here, the cosmic rays having a shortest wavelength and higher energy, and while the radio waves have the largest wavelength and lowest energy. We can recognize the colors of the radiation in the region of the 400 nanometer to 800 nanometer only. We will see all the colors only in the visible region, and the visible region lies in between 400 to 800 nanometer. See here in this figure shows the visible region. The region is called as visible region. In spectroscopic methods, UV, visible, IR, microwaves and radio waves are used. If we use the term light waves, then it is called as or implies the visible. If we use the form radiation, it implies the region from cosmic rays to the radio waves. Thus, the light waves are the electromagnetic radiations in the visible regions. Here see here, it is showing the cosmic rays to the radio waves. the energy increases from radio waves to cosmic rays, and wavelength it is decreases from the radio waves to cosmic rays. Now see here the next one, that is the regions that here has given from the gamma rays to the radio waves. First of all, we have to see here the gamma rays. Now gamma rays, these are the extremely high frequency waves or the smallest wavelengths, and carry a large amount of energy of any other waves. That is, you have to compare with the UV, IR, microwave and the radio waves in the electromagnetic spectrum, and these are given off by the stars and by the some radioactive substances. Now the next we will see here the X-rays. Majorly we have heard the X-rays in the hospitals. They are very high frequency waves and carry a lot of energy. They have a smaller wavelengths and having a higher energy than ultraviolet waves, that is the UV radiations, or you can say the microwaves, IR and the radio waves. But smallest frequency as compared with the gamma rays energy than gamma rays. They will pass through most substances, and this makes them useful in the medicine and industry to see inside things. That is the X-ray which are used in the medicine as well as industry to see inside the things. Now next we will see here the UV radiation. The UV radiation is also called as ultraviolet radiations. It is the radiations with the wavelength shorter than the visible light but longer than the X-rays. See this figure, what it indicates. In this range of 10 nanometer to 400 nanometer. Though these waves are invisible to the human eyes, some insects like the bumblebees can see them. They are responsible for causing our sunburns. Now this is the UV radiations. Now the next radiations, you see the visible radiations. The visible radiations, we can see all the things. It is a part of the electromagnetic spectrum that can be detected by the human eye. The visible spectrum as is actually made up of the whole range of colors mixed together, known as R2V, that is a red to violet the color. Now the next one is infrared radiations. Infrared, in short we can say that IR radiations. It lies in between the visible and the microwave radiations in the electromagnetic spectrum. These shorter IR wavelengths are ones used by your TV's remote control, and far infrared waves we experience every day in the form of heat. Next one that we have to see here, the microwaves. We have used usually in our house, that is the domestic microwave oven. These are the basically extremely high frequency radio waves and are made by various types of the transmitter. Their wavelength is usually a couple of centimeters. In a mobile phone, they are made by a transmitter chip and an antenna in a microwave oven. The next one is that the radio waves. Now these radio waves, the waves in the electromagnetic spectrum that have a longest wavelength, and the lowest frequency are called as the radio waves. They are used to transmit the information from the antenna of a broadcasting station to the antenna of your radio or TV. Now today we will finish at this point, and next we will see the types of the excitations, then the molecular excitations, rotational, vibrational, electronics excitation, etc. Thank you very much.